Okay, so this week you are working on a lab that is in your lab book again, so we're back to that. And it's Lab 17. It starts on page 151 of your lab book. The title of the lab is Evolution, Hardy-Weinberg Equilibrium. And so at this point, hopefully you've read the introduction. So pages 151 to 152. We're going to skip activity 1 because we had to be there as a class in order to taste this paper and get numbers of who can taste and who can't taste. So we're going to skip that. We're going to go right to activity 2, which starts on page 154. And I'm going to give you a brief introduction here, and then I'm going to start the activity with you. And then you are going to finish the activity on your own at home. And then there are 2 things that you are going to hand in. The first is some data, and that's going to include the data table, which is the same as what's on page 155, but I've recreated it for you. So there's a assignment. It says data table and graph. And so the data table on page 155 is what you're going to hand in along with a graph of that data. Now, when you graph that data, you're going to put both the P and Q lines on the same graph. They're both going to start off at 0.5. Okay, and then hopefully one line increases, the other one should decrease. So you're going to put them both on the same graph. You can make this graph using Excel if you know how to use Excel, or you can hand draw it. But if you hand draw it, it has to be on graph paper. Okay, and then you'll upload right to that assignment. The second assignment that you're going to have are the population genetics problems that are on page 156. Those include questions 2 through 6. And you've had some practice with those already when we did chapter 18 in lecture. So hopefully you're able to get through those okay. You can refer back to those if you need some help. So let me start activity 2 with you. So here's the scenario. We are going to simulate an extreme case of selection in which the recessive phenotype is going to be selected against. And therefore, over generations, we are going to see allele frequencies shift. Okay, and so that's microevolution, right? So we're going to start off with this scenario. We've got a population of rabbits, okay? And these rabbits have 2 different phenotypes. They can be either white, which is the dominant phenotype, or they can be red, which is the recessive phenotype. Okay, now rabbits are diploid, and so white rabbits could be either, we're going to use the letter R for color. Okay, so white rabbits are either big R, homozygous dominant, or white rabbits might have the genotype big R, little r. Those would be our heterozygotes. Okay, so either one of those genotypes, big R, or big R, little r, is going to give you the white phenotype. Okay, now the other phenotype again is red. And so red rabbits are going to be homozygous recessive, and their genotype will be little r. Hopefully these terms are coming back to you. Okay, so we have 2 phenotypes, white and red, and there's 3 genotypes. So big R, little r, either of those give you the white phenotype, and then the third genotype is little r, and that's going to give you red. Okay, and so at this point, right now, there is an equal likelihood, really, of either phenotype. Neither has a selective advantage over the other. Neither is better adapted to the environment. Now, these rabbits are living in the Arctic tundra. They're on a sheet of white, okay, constant white background from the snow and ice. And so, again, up until today, there's an equal likelihood of the survival of either colored rabbits. And so, either color is equally as likely to reproduce. Okay, there is no selective advantage. Well, today, somebody introduced a new species to the environment. It's the hawk. Okay, and the hawk is going to be a visually oriented predator, and it likes to eat rabbits. Okay, and obviously being a white rabbit is going to be an adaptation in this particular scenario, right? You're on a white background, you're a white rabbit, now you're camouflaged from that hawk. And any of the red rabbits, which again are homozygous recessive, little r, they're going to be sitting ducks, right? They're going to stick out like sore thumbs. They're going to appear, bright red against this white background, and so our hawk is going to pick them up and eat them. And so they're going to have a lower likelihood of reaching reproductive age and reproducing. They're going to have a disadvantage now in this environment. Okay, so here's our simulation. We're going to take a paper bag. Hopefully you have a paper bag at home. And we're going to put into our paper bag our gene pool at the very beginning of this. Okay? And so our gene pool, the lab book tells you, is going to be made up of 50 red and 50 white alleles. So we have 100 total alleles in our population. And again, there's an equal likelihood of both alleles. Neither is an advantage at this point, okay, until that hawk gets introduced today. So I'm going to put into my bag 50 red things and 50 white things. And if you don't have things at home, you can take just a sheet of paper and cut it into little squares. And, hopefully maybe you have red construction paper and then white computer paper, and you can cut that up. Now, you're going to need more than 50 red things eventually. Not in this first round, but as we go on, you're going to need more than 50 red things. You won't need more than 50 white because that number, you're going to need more than 50 white things because that number is going to increase. And the red, representing the red allele, which is selected against, that's going to decrease, so you won't need any more of those. Okay, so to start off with, in our bag, we're going to put 50 white things and 50 red things. Okay, now my things that I have, which you would have had if you were in the lab, they're these little plastic, I forget what the lab book calls them, extrusions, I don't know. They're like cut up straws. Okay, so I'm going to put 50 red ones in this bag, and I'm going to put 50 white ones in this bag. Okay, so here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15, 16, 17, 18, 19, 20, 2, 4, 6, 8, 30, 2, 4, 6, 8, 40, 41, 2, 3, 4, 5, 6, 7, 8, 9, 50. So I got 50 white alleles, red alleles in this bag. And now I've got to get my white extrusions, plastic cut straws. Okay, and again, you can use anything that you have. It's paper, straw pieces. You're going to start off with 50 red and now 50 white. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Whatever you use, make sure they don't stick together. 21, 2, 3, 4, 5, 6, 28, 7, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40, 42, 43, 44, 45, 46, 47, 48, 49, 50. Okay? Hopefully I counted right. We will see. Okay, so now I have my gene pool. Okay, so my population is made up of 50 individuals. There's 100 alleles total in my bag. I've got 50 red and 50 white alleles. Okay, so to start off with, in your table, you can go ahead and you can record this. For generation number 1, again, we're starting off with 50 red and 50 white alleles. So what's the frequency? If we got 100 total alleles and 50 of them are white, then the frequency of the white allele is 0.5. Same thing is true for red. If I've got 50 red alleles out of a total of 100 alleles, then the frequency of the red allele is 0.5. So in your table, for generation 1, for your P value, you're going to put 0.5, and for your Q value, you're going to put 0.5. Remember, the frequency of the dominant allele is going to be P. And in this case, the dominant allele is the white allele, the capital R allele, and that's going to have a frequency of 0.5 at this point right now. And again, the frequency of the little r, which is the frequency of the recessive allele, or Q, is also going to be 0.5. Remember that P and Q always have to equal 1. Okay, so 0.5 plus 0.5 right now equals 1. Okay, so the total or the sum of both alleles has to come out to 1. That's what we got here. So here's my bag. The next thing I'm going to do is I'm going to shake my bag up. And I'm going to simulate reproduction. Okay, random mating here. Shake it up. Now I'm going to pull these out 2 at a time without looking in my bag. And as I pull them out, I'm going to make, I guess, 3 piles. We'll follow what the lab book says. So I'm going to make 1 pile of homozygous dominant white rabbits. Okay. My second pile will be offspring that are heterozygote, rabbits that are white, but they're carriers of the red allele. And then my third pile will be a pile of my rabbits that are going to be homozygous red. Okay. Rabbits are diploid, so I'm pulling out 2 of these little things at a time. So here's my first 2. And look, I pulled out 2 white alleles. So this is a homozygous dominant white rabbit. Another homozygous dominant white rabbit. So now I've got 2 white rabbits. Here's a heterozygote. So I pulled out 1 red and 1 white allele. So again, I'm making 3 piles. Another heterozygous rabbit. Okay, another heterozygous rabbit. Homozygous red rabbit, little r, little r. Pull out my next. I got a homozygote. Sorry, a heterozygote. Homozygous recessive red rabbit. Okay, and I'm going to keep doing this until I pull out all 50. Okay, so another homozygous red. I got my 3 piles going on. Heterozygote. White rabbit. White rabbit. White. Heterozygous white. Homozygous red. Homozygous white. I'm getting down to it. Homozygous red. Homozygous red. Heterozygous white rabbit. Heterozygous white rabbit. Homozygous red. Heterozygous white rabbit. Heterozygous white rabbit. Homozygous red. Heterozygous white. So again, you're going to do this after generation 2. The red rabbit. Actually, I might take this out twice with you. White rabbit. White heterozygous. White homozygous. White homozygous. White heterozygous. White heterozygous. White heterozygous. White heterozygous. Wow, lots of heterozygous rabbits. Heterozygous. Homozygous red. Hold out 3. Heterozygous. Couple left. Heterozygous. Homozygous white. Heterozygous. Homozygous white. Homozygous white. Homozygous white. Heterozygous. I got a red rabbit. A white homozygous rabbit. Heterozygous white rabbit. Homozygous red rabbit. Couple left. Heterozygous. Heterozygous. Oop. Heterozygous. Got one left. Heterozygous white rabbit. Okay, so now I've got my 3 piles. Now I have to figure out how many rabbits are in all 3 of these piles, and I will start with my red rabbits. So I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, so I pulled out 12 red rabbits. So if you could look at the top of page 155, if you want to keep track of your numbers, you'll have to get a separate sheet of paper, but you can see at the top it says record the number of each category below. It's nice to kind of keep a record. Again, we don't give you enough space here, which something in the next edition of the lab book will. But you're going to record your numbers, okay? So if I have 12 red rabbits, how many red alleles are represented here? It would be 12 times 2, right? So that's 24 red alleles. Okay, I like to keep track of everything. I'm going to put my red alleles over to the side. Those are my red rabbits. I'm not putting them back yet. I'm just putting them over to the side. Okay. Ooh, I dropped one. There it is. Okay. So now what I'm going to do is I'm going to count up my homozygous white rabbits. So let's see. I got 1 rabbit, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I got 12 white rabbits, okay? So for white, at the top of page 155, I'm going to write down, what did I say, 12? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, yes. So 12 white rabbits. So again, that's 24 white alleles. Okay. So if so far I have 10, 24 offspring. Okay, I got a lot of heterozygotes here. How many? If I've got 24 of the others, how many should I have? If I've got 50 total offspring. Okay, we'll count them up just to be certain. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. Perfect. So I put the right stuff in the bag. So you're going to put 26 red, white rabbits. And so how many alleles is that? That's going to be 26 white alleles and 26 red alleles. Okay? So in total, I got 100 alleles here. I've got 50 offspring. And so in total, again, that's going to be 50 white alleles and 50 red alleles. And so I did everything right. I put the right stuff in the bag to start with. Okay, so now here is the tricky part. So what we're going to do is we're going to take all of those homozygous recessive red rabbits and we're going to kill them. Okay, so that hawk that we just introduced is going to eat up all of the homozygous recessive red rabbits. Okay, so if you look at your numbers here, that's 12 rabbits or 24 alleles that are going to be taken out of this population. Okay? And so if you go down on page 155, it tells you what to do next. So it says, after the removal of the red pairs, you now have to calculate the number of surviving alleles in the gene pool. Okay, so if we started off with 100 alleles, and we wiped out all of the red rabbits, that's 24 alleles. And so what are you left with? 76 alleles. Okay, we've got 76 alleles remaining in the population. Okay, so let's go down to part B. It says, you know that the hawk Get my calculator ready here. You know that the hawk did not kill any rabbit possessing a white allele. So the white rabbits that are homozygous dominant, white, right, big R, or heterozygous, white, red, or big R, little r, okay, they're going to survive, okay? These white rabbits, whether it's a homozygous white or a heterozygous white rabbit, it is protected from the hawk because it contains that white allele, okay? You started this first generation, generation 1, with 50 white alleles. So there are still 50 white alleles because you didn't take any away. Okay, so you can figure out P. Okay, how do you do that? You take 50, that's the number of white alleles that you started with, divided by the number of alleles that are left, which we just said, there's 76, right? If we lost 24 red alleles from our original 100, there are 76 alleles left in the population. So you're going to do P equals 50 divided by 76. And that's going to give you a run-on decimal. We're going to round this to the nearest tenths, okay, because we're working with these pieces that we have to be able to put in one. We can't put a decimal, a fraction in. So we're going to round to the nearest tenths place, okay? So on my calculator, it says 0.065789. Okay, so I'm going to round to the nearest tenths. So I've got a 6 there, but I have a 5 next to it, okay? 5 or above, give it a shove. You may have heard of that, right? So if it's 5 or higher, we're going to round up. If it's below 5, we're going to round down. So it's going to be 0.7. So for generation 2, in our table, you're going to put for P 0.7. What are you going to put for Q? Hopefully you said 0.3. Why? Because P plus Q have to equal 1. So to figure out Q, you would do 1 minus P, right? We're using the Hardy-Weinberg equation. So 1 minus 0.7 is 0.3. So for generation 2, in your table, you should have 0.7 for your P value and 0.3 for your Q value. Okay, so now we're going to go ahead and we're going to repopulate our gene pool. This is a very important next step. What are you going to put back in this bag? You want to bring your gene pool back up to 100. Okay, that's the only way this is going to work. Okay, because the frequency, you want the allele frequency to equal 100, okay, percent, or 1. And so into this bag, you need to put the right number. And so you just told me your frequency of P, or the white allele, is 0.7, or 70% of the alleles in the gene pool should be white. If there's 100 alleles total, how many are going to be white? What am I putting back in this bag? 70, okay? Math's nice and easy because we're putting 100 in, okay? So I'm going to put in 70 white alleles, and I'm going to put in 30 red alleles. Okay, I'm going to do this with you again out to this third generation, then I'm going to let you take it from there. So I told you you're not going to need any more red alleles than 50, right? That's what we started with. Now we just need 30, but your white alleles you will need more of, okay? So you can't just use the 50 that you may have already made, because now you need 70. So what I'm going to do is I'm going to take all of my white alleles that I already counted out, and I'm going to put them back in here. And I just have to add now 30 whites. Okay, try to make my life a little easier here. Almost there. Okay, so I got 50 whites in there. I need to put 30 more, right, because I want 70. Sorry, 20 more because I want 70. I'm thinking about the red alleles. So I got 50 white alleles in here. I'm going to get to 70, so I need to add 20. So 2, 4, 6, 8, 10, I'm just adding the little white things, okay? 12, 14, 16, 18, 20. Okay, so now in my bag, in my gene pool, I have 70 white alleles. Okay? Now I need to add in here 30 red to bring it up to 100 alleles. Okay, so here I go. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. Okay. So I've got 70 red alleles, and I've got 70 white alleles and 30 red alleles in my bag. Okay, so right now inside my bag, if I looked at allele frequency, the frequency of the white allele, or P, is 0.7, 70% of the 100, right? And my frequency for my recessive allele, or Q, or little r red, is 0.3, so 30%. So 70 white alleles, 30 red alleles. Okay, now I'm going to shake my bag and simulate random mating. Okay, and that hawk is flying overhead, just waiting for my red rabbits. And again, I'm going to pull them out 2 at a time. Okay, so bear with me here. Heterozygous, he's going to live. Homozygous white, going to live. Heterozygous white. Homozygous white. See, if we were together, you could be tallying up the numbers for me right now. Homozygous white. Heterozygous white. Nope. No rabbits have gotten eaten yet. Homozygous white. Heterozygous white. Homozygous white. Homozygous white. 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 Heterozygous white. No red rabbits. Ah, I spoke too soon. Whoop. Maybe not. Where'd it go? Okay. My first homozygous red rabbit. Heterozygous white. Homozygous white. Homozygous white. Heterozygous white. Ah, another red rabbit. So there's 2. Homozygous white rabbit. White rabbit. Heterozygous white. Heterozygous white. Pull that a third. Homozygous white. Heterozygous white. Heterozygous white. Homozygous red. Heterozygous white. Homozygous white. Red rabbit. White rabbit. Ooh. Red rabbit. Red rabbit. White. 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 Heterozygous white. Heterozygous. White. Getting down to it. Heterozygous white. Homozygous white. Heterozygous white. Heterozygous white. Heterozygous white. homozygous white. Okay, there it is. There's my rabbits. So again, we're going to count them up. So for my red rabbits, I got 1, 2, 3, 4, 5, 6. So again, you have to kind of reproduce what's at the top of page 155 for yourself. So my red rabbits, I just said I have 6 red. And so that is how many alleles? 12 red alleles are right here, okay? Before we go any further, you know that these rabbits are going to be eaten, right? And so if we started off in this bag with 100 total alleles, we just lost 6 rabbits, or 12 alleles, okay? How many alleles remain? 88, right? So we lost 12 alleles, 88 remain. Okay, how did I get that? 100 minus 12, that's it. Okay? Okay, so we could actually just mathematically figure this out, but let's follow along like we were in the lab book before. So let's count up our white rabbits. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Running out of room in my hand. So 18 so far. Okay, 18, don't forget that number. 19, 20, 21, 22, 23, 24, 25, 26. I want to write that down. So I got 26 white rabbits. 26 times 2 will give me the number of white alleles in this rabbit. So 12, 2 times 2 is 4 ones. So 52 white alleles right here. Okay, so the only group of rabbits that we have left are the heterozygotes, which are white, red. And so how many are there? Let's see. We got 1, 2, oop, one fell on the floor. There's 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay, let's write that down before I forget. I'm just going to put these back here. Okay. So if I've got 18 of these, that represents 18 white alleles and 18 red alleles. Okay, so let's figure out how many white alleles are here. So 52 plus 18 white alleles. Perfect. Okay, so I started off in my bag with 70 white alleles, and still now, in my gene pool that I have out here on my table, I have 70 white alleles. And that makes perfect sense, right? Because the hawk didn't eat any white rabbits, only red rabbits. And so we didn't lose any white alleles. We only lost red alleles. And not all the red alleles, only 12 of them. We started off with 30. We lost 12 so far. So now with this data, we can figure out the generation number 3. We can figure out the P and Q values for that generation to start. So what do? We take the number of white alleles, which we just said was 70. That number didn't change. And we divide it by the number of alleles that are left right now. So again, we started off with 100 alleles. We lost 12 red alleles. That means we're left with 88 alleles. 70 out of the 88 are white alleles. The rest are red. So what's our new P value? P is going to equal 70 divided by 88. The number of P alleles divided by the total number of alleles left. And that answer, if I'm looking at my calculator, is 0.795 whatever. So again, I want to round to the nearest tenths place. And so I've got 0.79, so that's going to be 0.8. Okay, so my new p-value is going to be 0.8. What's my q going to be? 1 minus 0.8. Okay, so that's going to be 0.2. Okay, so now you're going to go on, you're going to figure out generations 4, 5, and 6. Let me help you get started on generation 4. You're going to have your bag, okay, representing your gene pool. And into the bag, what are you putting? How many white alleles? You got to go back to your chart. What did you just put in for the p-value? You just put 0.8, right? So that means you're putting 80 white alleles into the bag. 80 white little squares of paper. How many red squares of paper, red alleles, are you putting into your bag? Look back at your chart here, your table. You put 0.2 for Q. That's the frequency of the red allele. And again, we're only going to have 100 alleles in the bag. And so if 0.2% of them or 20% of them are going to be red, okay, you're going to put 20 in. Nice, easy math. So you're putting into your bag, to start off, you're putting in 80 white alleles and 20 red alleles. You're going to shake your bag up, and they're going to pull out alleles 2 at a time. You should end up with 50 offspring out on your table. You're going to separate them into 3 groups. Your homozygous dominant white rabbits, your heterozygous white rabbits, and your homozygous recessive red rabbits. After you separate them out, again, there should be 50 total offspring. You're going to kill off those red rabbits. You're going to figure out the new total number of alleles left. And of that, how many were white? And then you can figure out your new P and Q values. Okay, you always want to make sure your P and Q add up to 1. And you always want to make sure you're putting 100 alleles back into this bag. Okay, so again, you're going to finish this out up into generation 6. And after you have this table complete, you're then going to graph this data. And as you can see already what the trend is, they both P and Q start off at 0.5. So 50% of the alleles in the bag were white and 50% were red, okay, or a frequency of 0.5 and 0.5. And then you should see that that line for P, the frequency of the white dominant allele, should increase over time, and the frequency of Q should decrease over time. Okay, and so your graph, what it's going to look like is, if you can picture this in your mind, your x-axis should be generation number, so generation 1, 2, 3, out to 6, and your y-axis should be allele frequency. Okay, and again, it should go from 0 to 1, and both of your lines should start off at a frequency of 0.5. Okay, so after you're finished with the activity, your table will be done, and then you can go ahead and you can graph that table. And I also want you to think about this, and I didn't say to do this, but I'm going to change my mind. So part of the assignment, I told you to do population genetics problems 2 through 6 on page 156. I'm actually going to add in question number 1. I want you to think about this. So question 1 says graph the values of P and Q. You're going to do that. And then it says, what do you think the eventual fate of the recessive allele? So what do you think the fate of the R allele, the little r allele, the red allele, Q? What do you think the eventual fate of that allele is going to be? Okay, we know that it's decreasing. So the question is will that allele frequency ever get to 0? Why or why not? Okay, and if you're not, you got to make sure that you're actually doing the activity to really see this. Okay, will it ever get to 0? Why or why not? Okay. All right, so you've got to finish the table, graph your results, and then you're going to go ahead and answer that question along with questions 2 through 6, which deal with population genetics. Okay, that'll all be turned in, and that's it for this week. Okay, so good luck. Make sure you really do the simulation. Don't make up numbers because it won't come out right. Okay.